Okay, so today we're going to be talking about how to calculate the excess reactant. So, an excess reactant is the reactant that's opposite of the limiting reactant. It's if a limiting reactant is completely used up, then the other reactants are the excess reactants. So that is to say that you have excess reactant left over. Okay, so whatever reaction takes place, the limiting reactant runs out. The other reactants that are still there, those are the excess reactant. So what we need to be able to do is we need to be able to calculate how much of the excess reactants are still left. So there's a couple of steps in how to do this. The main thing is you need to start your excess reactant problem with either the moles of the limiting reactants or the moles of the theoretical yield. So here are the steps outlined here, but I'm just going to go and demonstrate them throughout a practice problem. I think that's the best way to learn it. Okay, so let's take this first example. We're going to make some sodium oxide. And in order to do that, we're mixing 3.5 grams of sodium and 10 grams of oxygen. First thing we need to do is convert what we have into moles. So we're going to take our 3.5 grams of sodium. The molar mass of sodium is 23.00. And we get 0.1521 moles of sodium. Not rounding the number yet because I'm not done with the problem. And then we have 10 grams of oxygen. Molar mass is 16 grams. Oops, and I just realized this is O2. So the molar mass is actually 32. Okay, 0.3125 moles of O2. Those are my two reactants. Okay, just like with other limiting reactants, we're going to solve for the product. So we set that up, the product being sodium oxide. And now we're using mole ratios. So according to the balanced equation, we have 2 moles of Na2O for every 4 moles of sodium. And we cancel the moles of sodium. So 0.1521 divided by 2. 0.07605 Na2O. Let's do the same for oxygen. 2 moles of Na2O for every 1 mole of O2. Moles of oxygen cancel. And we get 0.625 moles of Na2O. All right. At this point, we've solved for the amount of product from the perspective of each reactant. And we get these two yields, and what we know by now is that the higher one is not possible. So therefore, the lower one is the theoretical yield. The theoretical yield was determined by the limiting reactant. So the limiting reactant is going to be sodium. If the limiting reactant is sodium, that means that oxygen is the excess reactant. There is oxygen left over. So what we need to do now is we need to figure out the rest of this problem. We need to figure out how many moles and how many grams of the excess reactant were still left at the end. So to do this, we need to start with either the limiting reactant moles or the theoretical yield moles. I think either one works. I'm just going to use the theoretical yield moles here. So I'm just going to start the next line of work here and say, all right, 0.07605 moles of sodium oxide were made. So what we want to do is we want to work backwards using a mole ratio, and we want to solve for the amount of the excess reactant that was actually used. Because I know how much the limiting reactant was used, all of the limiting reactant was used. I want to know how much of this was used. So let's solve for O2 in the top. 1 mole of O2 and 2 moles of Na2 go in the denominator. Okay, so 0.07605 divided by 2. So what we get now is 0.03753 moles of O2. And this is important to write the label here, used. That's how many moles of oxygen were used. So if we think back to, or we look back to how many moles of oxygen you had at the beginning, right? We had this many moles of oxygen at the start, but we only used this amount of moles. So we can clearly see how much is left over. All we need to do is subtract. So 0.3125 moles of O2 at the start minus 0.03753 moles of O2 at the end. And actually, you know what? I need to clean this up a little bit because now I have changed. I've done all these multiplications, but now I'm doing a subtraction. And the original number would only allow me to have 3 sig figs. So I'm going to drop that 3 there, drop that 3 there, and this becomes a 3. So because I am now subtracting, the rule for subtraction is decimal places. Okay. 0.313 minus 0.037. So we get 0.2755 0.276 moles of O2 are excess. And that's how we determine how many moles of the excess reactant there were. And of course, we could turn this into grams, right? If you multiply by the molars, if you want to. So mole, oops, we're canceling moles, so we're going to be multiplying by molar mass. Excuse me. 8.82 grams of O2 are excess. All right, so let's review the steps that we did. First and foremost, balanced equation. Take the givens, convert them into moles. There's 2 reactants here, convert them each to moles. If there were 3 reactants, it doesn't change anything. You turn all 3 reactants into moles. Next step, use the mole ratio to solve for a common product. In this case, there's only one product, so we chose Na2O. So 2 moles of Na2O, we're canceling the moles of Na here. 2 moles of Na2O, canceling the moles of O2 here. You should arrive at moles of the same product, Na2O, Na2O. The 2 values you have here, you go with the one that is lower. That is the one that is actually possible. That is your theoretical yield. Your theoretical yield was determined by the limiting reactant. Once you've determined what your theoretical yield is, start another flow of work here. Start with that. And now you're solving for the excess reactant. You're solving for that was O2. You're solving for oxygen. So solve for the moles of oxygen, and this is the amount that was used. You're going to take this amount, you're going to subtract it from the starting amount. Remember, the starting amount is what you determined at the beginning of the problem. And the difference is how much is excess. That is the amount that is left over. So this is how you figure out. Now, if there were 3 reactants, that means you would have 2 excess reactants, because there's always only one limiting reactant in a problem. So you would still start the other reactant, the 3rd reactant, with this and do the same kind of workflow. Solve for the amount of that reactant and then subtract. Okay, so let's just see if we've got this down. I'm going to create a problem from scratch, and then we're going to see if we can find the excess reactant for this one as well. Okay, so let's say we've got zinc plus sodium phosphate. This is just an example, not whether this reaction would actually happen or not. Okay, so if this reaction takes place, this is going to be a single replacement. We're going to combine zinc with phosphate based on charges. This is what your formula would be. Okay, so we balance this. We need 2 phosphates, we need 6 sodiums, and we need 3 zincs. Okay, so this is balanced now. All right, so let's say that we had 10 grams zinc and, I don't know, let's say 50 grams of Na3PO4. Okay, step 1, convert to moles. Zinc is 65.41 grams. So this would be 0.153 moles of zinc as a reactant. Or sodium phosphate. 23 times 3 plus 30.97 plus 64. So this is going to weigh 163.97. Okay, find moles. 0.305 moles of sodium phosphate. Okay, so let's say the goal is to collect this. That's our goal. So if that's our goal, if that's what's being collected, we want to solve for that as our product. So for every 1 mole of zinc phosphate that forms, and now I have to cancel zinc, 3 moles of zinc are required. Is everybody seeing where that's coming from? We're using those numbers from the balanced equation here. 3 of these, 1 of these. That's where these come from. All right. And so 153 divided by 3, 0.0510 moles of zinc phosphate. All right, let's do the other reactant. So for the sodium phosphate, there's 1 mole of zinc phosphate for every 2 moles of sodium phosphate. Again, those numbers taken from here. Okay, let's calculate. We get 0.1525. Okay, so these are my 2 yields of the same product, zinc phosphate, but as we discussed earlier, the lower one is the theoretical. So this is our theoretical yield. This is our limiting reactant, which makes this our excess reactant. Sodium phosphate is our excess reactant. Okay, so now let's, the problem also would want you to calculate this into grams. That's not the focus right now. You guys know how to do that by now. I'm going to move on to find the excess reactant. Okay, to find the excess reactant, start with your theoretical yield in moles. 0.0510 moles of zinc phosphate, and back solve for the sodium phosphate using mole ratios. So the excess reactant was sodium phosphate, so 2 moles of Na3PO4 for every 1 mole of zinc phosphate. Okay, so 1 times 0.102 moles of Na3PO4 used. Recall that this is the amount that we had initially. So 0.305 moles of sodium phosphate at the start minus 0.102 moles of Na3PO4 used. So 0.203 moles Na3PO4 excess. And we're done. Unless they want it in grams. Because if they want it in grams, then you go one more step and convert it. But that is how you do excess reactant problems.